All right, so today is kind of the second introductory lecture, and we're going to go into a little bit more detail about energy systems, kind of broadly, and then a subset of that, which is electricity systems. And then eventually we'll get to even a subset of that, which is kind of the distributed energy resource view that we take in this class. Today will be a little bit more technical, but still I'm not going to throw a ton of equations and stuff like that at you. But starting next week, there will be kind of more mathematical and programming type content coming at you. Um, so we'll start today by just a little bit of background, talking about units of energy and power. If you work in the energy industry, like it's just a whole bunch of your job will be unit conversions, especially if you work in the US, where it's common to use English units as well as metric units and mixes of the two. So we're just going to go over real quick kind of how all that stuff works. I think this should be a review for everybody, but we'll use some weird units later in the lecture. So I just want to kind of do some level setting and make sure everyone understands that. We'll talk about energy and we'll talk about electricity, and then we'll talk about, again, some motivation for DERs. And I think this should make a little bit more concrete some of the themes that came up in the reading and the listening that you guys did yesterday. So this stuff I'm going to go through a little bit quickly because there's a fair amount of content today, but in the metric system, sort of the easy system to work with in energy and power, and the system that you would work with in most places in the world other than the US, the basic unit of energy is the joule, which is defined as 1 Newton meter. So this comes basically from the definition of work. You can remember it in that way. So a joule is basically the work that is done when a force of 1 Newton acts through 1 meter, basically. And then the basic unit of power is just energy per unit time. So the basic unit of power is the watt, which is defined as a joule per second. And when we convert between units, the basic way to remember how to do unit conversions is you take the units that you have and you multiply by something that is equivalent to 1, a ratio equivalent to 1. And the way we get those ratios is you can always go back and say, okay, what is the definition of this thing? Well, 1 hour, that's equal to 3,600 seconds, right? 60 seconds in a minute, 60 minutes in an hour, and you get this ratio. Okay, so then if you divide one side of this equation, or both sides of the equation by the 1 hour, you get 3,600 seconds divided by 1 hour is equal to 1. Very simple. Everybody obviously knows this, but you can also do this in weirder, more complicated unit conversions. So another example, we could do the definition of a watt. Okay, if you divide both sides of that equation by, let's see, the 1 watt, we get a joule divided by 1 watt second, right? So the product of a joule per second and a second is equal to a joule. So this thing here is also equal to 1. So just as one example, one unit that we very often use when talking about electricity is the watt hour. So that's a unit of energy, and it's basically if you have, say, a 1 watt light bulb, a little LED light bulb, and it runs for an hour, it would use 1 watt hour of electricity. So here, to convert a watt hour into joules, we multiply by something equivalent to 1. Here, this is the time conversion. The hours cancel here, and then we have 3,600 watt seconds. And then we can again multiply by a ratio equal to 1, and the watt seconds cancel, we get joules. So very straightforward in this example, but again, like keeping your hat on through unit conversions is sometimes challenging work that we do. It's super challenging, but it's easy to mess up. So important to go back to basics, I think. And then we'll talk in this lecture, we'll use some scientific prefixes here. So we'll talk about exa, which means 10 to the 18th. So we will also talk about petajoules, 10 to the 15th joules. Terajoule, this is a trillion joules. Giga, this is a billion, and so on down the line. And so this, I think you can always just look this up on Wikipedia or whatever, but I wanted to mention it because we'll use, for example, exa and peta today. And then there are various scales of power that we will talk about in this class, ranging over many, many orders of magnitude. So if we look at all of the solar power that the Earth basically receives from the sun, from sunlight transmitted through space, that's equal to 170 petawatts. So this would be about 2 times 10 to the, let's see, peta is 10 to the 15th, and we have about 200 of those. So that's about 2 times 10 to the 17 watts. And then all of the energy that humanity uses, if you take all the energy we use in a year in all forms, electricity, fossil fuels, everything else, and we divide it by the number of hours in a year, we get about 20 terawatts of kind of continuous time average energy consumption. And so that's for all of humanity. So the difference between what hits the Earth from the sun and what we actually use for all human activities is about a factor of 10 to the 4 difference between these two, right? This is 10 to the 17, 20 terawatts. We can go back to tera. Well, that's 10 to the 12. So this is 10 to the 13 here. So between 10 to the 13 and 10 to the 17 is 4 orders of magnitude, or 10,000. So 10,000 times more energy hits the Earth from the sun than all humanity uses for all purposes. Okay. Electricity generation globally is about 9 terawatts. So compare that to the roughly 20 terawatts that we use from all forms of energy. About roughly, I guess, 15% of all of the electricity generation capacity in the Earth is in the United States. So we have about 1.2 terawatts of electricity generation capacity here. So US is roughly 4% of the world population, 335 million people here in the US and about 8.2 billion in the country. So 4% of population, but 15% of electricity generation. I don't know, kind of interesting. Here in the state of Indiana, so the peak electricity demand, if you look at kind of in the most energy intensive hour of the year, in that hour, we're using about 20 gigawatts, 20 billion watts of power. So this, I don't know what, 20 divided by 1.2, roughly 2% of total US electricity generation capacity. The biggest single generator on the grid, it's not precise, but roughly nuclear power plants or some huge coal or natural gas power plants, or even some really, really big hydro power plants can be kind of at the scale of a gigawatt or maybe 2 gigawatts. I think the biggest electricity generator in the world, last I checked, any guesses at that? What the biggest single power plant in the world is? Rush?
Not sure, but maybe China's dam.
Yeah, so last I checked, it was the Three Gorges Dam in China, which I think has a capacity of like 13 gigawatts. So just enormous river, right? I think it's the Yangtze River that is dammed. And, yeah, so it's quite big. Then the city of Lafayette here at peak, kind of this probably happens on the hottest afternoon of the year when we're using a ton of air conditioning and also businesses and people are active, about 350 megawatts. So compared to a nuclear power plant, this is, you could power basically 3 greater Lafayette areas with 1 nuke plant. An electric vehicle, when you're flooring it in something like a Tesla Model S, which can go 0 to 60 in about 3 seconds. If you look at how much power is being discharged from the battery, so stored chemical potential energy all the way through kinetic energy of the vehicle, you get about 400 kilowatts. So this is roughly a factor of 1,000. So if you had 1,000 Teslas flooring it, they would use as much power as being used at peak by sort of all people and all activities in the greater Lafayette area. Central air conditioner for a house might use on the order of 5 kilowatts, and an LED light bulb might be around 10 watts. So here we've gotten down to 10 to the 1 watts, and up here we were at the order of 10 to the 17 watts. So I guess that's 16 orders of magnitude difference in the kind of energy scales that we're looking at. So not all of these are relevant for what we'll be doing in the class, but I think they are kind of interesting to wrap our head around. And of course, so in this class, we'll use SI units throughout. But if you go to work in the energy industry, you will quickly find that SI units are actually kind of a rarity here in the US, although they are used. So the non-metric unit in the English or the foot-pound system is the basic one is the BTU, the British thermal unit. And that, if you do a unit conversion, is equal to 0.293 watt hours or 1055 joules. And then there are many, many other units of energy, and I'm just kind of putting up here a bunch of them for reference for you guys. I do not expect you to memorize all of these. But for example, the calorie that we talked about with food, you can work out conversions there into BTUs. A therm, this is a unit that's used often in measuring energy content of natural gas. So that's equal to 10 to the 5 or 100,000 BTUs. MMBTU, this is million BTU, goofy prefix here in the English units. Sometimes we talk about tons or megatons of explosion, not in this class, but in other applications, you might talk about that. We won't be blowing up too much TNT, but this also is a unit of energy, and it's equivalent to the unit of energy that 1,000 kilograms of TNT releases, converts from chemical potential energy into kinetic and thermal energy when it explodes. And then there's barrels of oil equivalent and so forth. And we will talk about actually quads, quadrillion BTU or 10 to the 15 BTU. And one quad is roughly equal to 1 exajoule, so 10 to the 18 joules. Okay, and then there are units of power in the non-metric system as well. One is the BTU per hour, probably the most common one that you would see working in something like a heating or cooling industry. or electric power industry. But there are others, the horsepower, and actually a ton of cooling. This is one that shows up sometimes in air conditioning and refrigeration industry. So this is defined as 12,000 BTUs per hour. And it's also basically the amount of thermal energy that's absorbed when a ton of ice melts over the course of one day. So if you take that energy, divide it by a one-day time span, on average, it's equal to a ton of cooling, or 12,000 BTUs per hour. Okay, so people kind of make fun of the English unit system, and it is kind of goofy, and it sounds kind of antiquated, like you're talking about how much work a horse can do in an hour, or things like that. But actually, I think it's kind of nice, because the convention in the English system is to use different units for different like types of industries or activities. So you might use a ton of cooling when you're talking about refrigeration, and you might use BTUs when you're talking about, say, the thermal energy put into a power plant. And so if you want a conversion between those, rather than just having a dimensionless efficiency like you would have if you were going from joules of chemical energy to joules of thermal energy, you would have a conversion factor that's something like BTUs per ton. And so the units actually carry information about the kind of energy or the kind of process that you're talking about, which sometimes makes it easier to wrap your head around what's happening in a problem. All right, so with that stuff under our belt, we can move on to talk about energy in the United States. And I think it's important always to ask, why do we care about this? Why is it worth studying? When we talk about energy, I think it's important to remember that today, about 80% of the energy system is, at least in terms of what's called primary energy, and I'll talk about what that means in a second. But really, the vast majority of energy that we're talking about is fossil fuel energy. And so why might we want to talk about fossil fuels? Well, today, fossil fuels have pretty significant impacts on humans. So there are a couple of recent papers that try to characterize from outdoor air pollution, things like fine particulate matter, small particles, dust, and things like that, that's released when you burn fossil fuels. When people breathe that stuff, it causes a variety of health issues, ranging from heart problems, cancers, brain issues, and strokes, things like that. And about 5 to 10 million deaths per year, depending on which scientific analysis you look at, can be attributed to burning fossil fuels and causing either indoor or outdoor air pollution. So about 60 million people die worldwide per year. So we're looking at kind of 8 to 16%, something like that, of all deaths can be attributed to fossil fuel pollution. And this is not getting into water pollution and things like that. This is just from breathing things. And about 3/4 of the climate greenhouse gas emissions that are emitted from fossil fuel energy systems. Okay, so that's sort of environmental motivations. There are also economic and political motivations for studying energy. So humanity gives each other, right? There's an exchange of about $6.5 trillion per year for energy. This is all the electricity, all the fuels that we buy and sell. So this is an enormous transfer of wealth, basically from almost everybody, all the people who pay utility bills, who gas up a vehicle, things like that, to the comparatively small number of people who own and have major investments in fossil fuel companies. So there's a lot of wealth transfer that basically concentrates wealth in a small number of hands. And then energy has influence both on domestic politics, but also on international politics. So, for example, the oil trade, OPEC and Russia and things like this, they come up very often when we talk about geopolitical conflict and things like that. So that's not my area of expertise, but I think it's interesting and an important dynamic. And then energy, these are all bad things, potentially some good things, a lot of money to be made. If you can do something that saves 1% of energy costs, you can be a billionaire within a year. But also, it has some significant influences on what we consider human development. And there are many ways to kind of quantify human development. The United Nations has one that they call the HDI, the Human Development Index, which is basically a 3-part index that takes into account access to knowledge, access to good healthcare and long, healthy lives, and then basically quality or standard of living measured by income. And so if you take those three, and you kind of do an appropriate weighting mixture of that, you get the Human Development Index. And so here is a plot of HDI, this UN metric of human development, versus average energy use per person in units of terajoules, so trillion joules per year. And each of the blue dots on this plot is one country in 2019. So we chose 2019 because it kind of was the last data that was unaffected by the coronavirus pandemic. So you have developing nations down here. At this end is actually almost all petrostates. So countries that a huge portion of their economy comes from fossil fuels. So Qatar, Saudi Arabia, and the US is actually up here. Canada and Norway are also kind of out here. And then there's a cluster. This is many European and Asian nations that are kind of in this 0.15 to 0.25 terajoules per person per year. So anyway, the main trend here is that as energy use increases, there's a correlation with Human Development Index. So health, knowledge, and income tend to go up with energy use to a point, and then we kind of see a plateau. And above that, increasing energy use may increase wealth, may increase inequality. So you may see really rich people and also really, really poor people, but the overall outcomes within a nation tend to sort of no longer be correlated with energy use above. Okay, I'm going through a lot here and I want to get to the kind of core material for the class. So I'm just going to blaze through a couple of sections and then we will slow down and have a little bit more detailed discussion here. But so this is a plot of primary energy sources over time in the United States. And here primary means basically the input energy. So if we look at coal, for example, it's a hydrocarbon, and stored in the molecular bonds within that hydrocarbon is a lot of chemical potential energy. And when it undergoes a combustion reaction, it releases, in an exothermal reaction, releases a lot of that energy. And maybe in a coal-fired power plant, only about 1/3 of that energy would be useful for electricity. So the primary energy, though, includes the 2/3 that basically would get exhausted to the environment as waste heat. So this is all that chemical potential energy that's in the fuels. Anyway, you can see over time here from 1990 to I think 2023, we have nuclear in the bottom here has been roughly constant. We haven't built a lot of new nuclear, a little bit, but also we've had some nuclear retirements, and so this thing stays roughly flat. Oil also has been kind of roughly flat in the US. One of the major stories in US energy kind of over my lifetime is that coal has been winding down slowly, but steadily over the last roughly 20 years. And it's been displaced essentially by natural gas. You can see that the brown wedge here is growing over time, and renewables. And I'll show another graph here of what this renewables wedge is, but you can see that it's kind of growing, since roughly in the last 20 years, it's maybe doubled. So I just want to make the distinction again a little bit more clear between primary energy and then what's called final energy, which is sort of the useful energy that provides services to people. So this is what's called a Sankey diagram, and this one was made by researchers at Lawrence Livermore National Laboratory, a big Department of Energy lab. And on the left here, we have all the sources that kind of go into the US economy. And the numbers here are in quads, which is again quadrillion BTUs, which one quad is roughly equal to 1 exajoule. So 10 to the 18 joules. And the overall energy sort of size of the US economy is about 100 quads or 100 exajoules, so 10 to the 20 joules. So we can see, for example, that petroleum here is used almost entirely in the transportation and the industrial sectors. Basically, very, very little petroleum goes into the electricity generation sector. So we don't really use oil for electricity. This is true now. It wasn't true in the 1970s, for example, but this has been one change kind of over the last roughly half century. But anyway, so you see that even in the transportation sector, oil comes in. There's conversions here from refining, to make gasoline and diesel, and then it gets burned. And we can see that only a small portion of it actually turns into useful energy that moves vehicles down the road or moves planes through the air. And a lot of it gets turned into what we call rejected energy or waste heat, basically. So the engines in automobiles that burn fuel are typically maybe 20 to 30% efficient. So the remaining 70 to 80% basically just goes to heat up air on the highway. And we see similar things in the electricity generation and so on. So the main point here is that actually 2/3 of the input energy, the primary energy that goes into the economy, ends up just as waste heat. It doesn't provide services that are useful to humans. And about 1/3 is the energy services. So if you think about a transition over the coming decades that replaces fossil fuels for many uses, one of the interesting features of that transition is that it would greatly reduce this waste heat here. Because something like an EV engine is about 80 or 85% efficient compared to maybe 20, 25% in a combustion engine. Okay, so that's the distinction between primary energy, the stuff on the left, and then final or useful energy, the stuff on the right here. And again, just making this point, so why do we have roughly 2/3 of all that input energy, the vast majority, 80% or whatever of which is from fossil fuels? Why is so much of that wasted, roughly 2/3 of it? And again, because that's basically from inefficiencies and conversions from that primary energy to the useful final energy. So a gas or a diesel engine might waste about 3/4 of the input energy. Coal or a nuclear power plant might waste about 2/3. A gas power plant might waste half or more. And then even a furnace or a boiler that you would find in a building like this, or maybe the apartment building that you live in, typically might be somewhere between 70 and 90 or 95% efficient. So a lot of losses there as well. Okay, so then another big story, and we talked about this a little bit on Tuesday in the first lecture, but another big story of energy in the United States has to do with what's called fracking, hydraulic fracturing, and horizontal drilling. So this, as we mentioned on Tuesday, is kind of a major innovation that happened in the early 2000s and then caused both oil and gas production in the US to boom significantly. So just an illustration here of what this is. So historically, oil and gas companies typically got oil and gas from what are called loose rock formations, which means they're porous, meaning there's like lots of holes. If you zoom into a rock, it would have a lot of empty space, and also permeable, which means that a fluid can transfer, move between the different holes, the different pores pretty easily. So basically, this is where fluids and gases can move easily through the rock. But a lot of those resources, were very ample in kind of the early 1900s and became more and more scarce as we extracted more and more of the fossil fuel from them over the years. But then this innovation around 2005 basically was two things. One is that companies learned how to drill horizontally. So that was not a thing that was easy to do technologically before about the year 2000. And then the other is hydraulic fracturing, which again has to do with putting down high pressure fluids and then using them to crack rock, to basically take tight rock that's not porous, not very permeable, and bash it open to make pores and allow permeation of fluids through it. So the idea is that you smash a bunch of rock and then you more or less get natural gas and or oil coming back up out of the well. And due to that innovation, we can see again around 2005, we have this major takeoff where the dark curve here is the fracked oil and gas. And the percentage on the y-axis here is the percent of total oil and gas energy production in the US. So you can see in 2000, it was 100% not fracked stuff. And then by basically 2020, we had about 80 or 85% coming from this hydraulic fracturing and horizontal drilling combination. Okay. And one of the results of that is that the exports of United States oil and gas have gone up a lot, kind of in the last 20 years. So the US basically didn't export any oil. In fact, it was federally not allowed. This is for what we call energy security purposes, basically trying to protect the US economy, make sure we have enough oil and that the oil is inexpensive enough for the uses that we need it for. And then those actually toward the end of the Obama administration, those were relaxed. And now the US is among the largest exporters of both oil and natural gas in the world. And these things are typically not accounted for in emissions. So if you look at what the EPA estimates from US emissions, it includes only stuff like fuels that are burned within the borders of the US. So fuels that we export and people burn in other places don't show up in that accounting. Okay, so that is energy broadly. Let's drill down a little bit and talk about electricity more specifically as kind of the interesting subset of energy that we will mostly focus on in this class. So again, why do we care about electricity? Why might we want to study it? Well, one reason is that it is either essential or very convenient for many applications, many things that we like to do in our lives. So if you look at what people first started to do with electricity in the early days, a lot of it was lighting, to extend the days that you could be awake and do interesting stuff and do work and things like that, extend the hours that you could do that. Another is pumping water for clean water supply within cities, but also for sewage treatment and things like that. A lot of medical devices, diagnostics, but also treatment devices depend critically on access to electricity. So something like a dialysis machine or a ventilator, you're probably not going to power that with fossil fuel. And then all our consumer electronics and the TVs and video games and things like that we like for fun. So I think there's an interesting illustration of kind of a thought experiment coming from a car commercial from 10 years or so ago. But I just want to show this really quickly.
What if everything ran on gas?
Okay, so that's a Nissan Leaf, an electric car commercial from, I don't know, whatever, 2005, 2010, something like that. But anyway, I think it's interesting to think, what if we didn't have electricity and we had to use fuels for kind of everything else in our life? And electricity is also interesting. So we talked about how it's pretty crucial for climate action. How one popular approach, the one that, at least for now, the US is embracing. This may change in a week when the administration changes, but the basic idea here, and other countries around the world are using this as well, is to try to clean up the electricity generation sector and then build it out, expand it so that we can use all that clean electricity for other things, for transportation, for heating, for cooking, and things like that. And then I think that the electricity sector is just a fascinating intersection of disciplines. So certainly there's a lot of technical work that goes into understanding electricity from many engineering disciplines. Electrical engineering, obviously, but also mechanical engineering has a lot to do with construction of power plants, vehicles, things like that. Industrial engineering and operations research, I think, are crucial in this field. Civil engineering, major civil works, things like huge dams, nuclear power plants, tons of concrete, important structural considerations there. Nuclear engineering, obviously, computer science, there's a lot of algorithmic work that goes into kind of operating and managing power grids. But beyond engineering, it also involves a lot of economics. And we'll talk a little bit today about some of the economic organization and the business organization of the electricity sector. And it's also deeply involved with policy. So the sorts of laws that Congress and the president make influence the landscape of energy, but also at the state and municipal levels, there's a lot of involvement in government in sort of regulating and overseeing electricity supply and distribution. So just again, some background and trends. This is United States electricity use by sector over the years from 1950 all the way through 2020. And it's broken out at the bottom here is the industrial sector, basically, factories, refineries, things like that. The commercial sector, so this is office buildings, hospitals, things of that nature. The residential sector, essentially all of our apartments, condos, and houses. And then direct use on top here would be something like a factory that has an on-site electricity generator, maybe a natural gas generator, or maybe an office building or a house that has solar photovoltaics on the roof and uses that sort of behind the meter rather than feeding it out into the broader electricity grid. So you can see electricity use increased a lot until about year 2000, 2005, and then it kind of stabilized. So we've not really been in an era of growing the electricity grid or how much electricity we use for the last roughly 20 years. And then here is electricity generation. Again, we have the same profile. Oh, I should note that the y-axis here, this is electrical energy supply, and this is in units of petawatt hours, so 10 to the 15 watt hours. And we see basically, again, oil and oil products were used for electricity generation quite significantly until, wait, I'm sorry, is this correct? Yeah. Oh, sorry, this is coal. Yes, the bottom of the coal there. Thank you. This light brown petroleum looks very similar to the dark brown for coal. And there's basically no petroleum used after about 2000. We still use a little bit of oil fire generation for backup and peaking power plants, things like that, but not very much. And then, so coal, we see ramps up and then ramps down around 2005, and it's displaced by natural gas significantly, but also by the green wedge renewables growing out somewhat over the years. And this nuclear wedge started really around 1970. So there was a lot of beginning of construction of nuclear power plants in the late 60s, but they didn't really come online until the early 70s. And then we continued to build through the 80s. And then by about 1990, we had more or less stopped building nuclear. I think one nuclear power plant has come on this century, Vogtle plant, and I forget how to pronounce it, Vogtle in Georgia. Yes, Suresh.
It depends on many different factors like politics and stuff like that, but what would the figure look like in 20 years from now?
It's a really good question. So for those online, what would this look like if we extended it forward through, say, 2050? And of course, then we're getting into scenario analysis. We don't have a perfect crystal ball, but we could imagine, under different policy scenarios, what this would look like. So yeah, it's hard to say exactly what trajectory we are on, but there are recent trends where this renewables wedge has been increasing significantly. You can imagine the coal trend continuing downward. So other countries that are a little bit further ahead of the US on coal phase out have gotten rid of coal completely. So in the UK, for example, the last coal-fired power plant shut down actually in 2024. So you can imagine this dropping out. This natural gas, I think there's a lot of question about whether this natural gas wedge would continue at about this size, would grow, or would shrink. And I think most scenarios that have an affordable and clean energy grid, electricity grid in 2050 have not very much of this. And what is there basically builds out carbon capture in order to basically take the CO2 that's emitted when gas is burned, put it back into pipelines, and ship it back into caves and rock formations and things like that to store it underground permanently, or at least for a very long time. But there's who's going to pay for an oil and gas company to capture all the CO2, which is expensive, challenging, right? It's hard to get high capture rates. It hasn't really been figured out at scale yet. And then there's a little bit of market for CO2 for things like carbonating beverages and for some industrial processes, but it's maybe 1% of all the CO2 that we need to be captured if we wanted to zero out emissions from natural gas. So the vast majority of it would need to be put into pipes and shipped around and stored underground. So that's a huge engineering challenge. It's quite costly to do at this kind of scale. Yeah, it would require basically taxpayer subsidy to do it. Yes.
Building upon it, the company that I used to work for a couple of months in Canada, they were trying to basically shift from natural gas to renewable natural gas, biomethane, and hydrogen.
Right.
So I guess that's also an interesting scenario for most of the companies.
Yeah, for sure. So again, for folks online, the comment is that in Canada, and actually a lot of people are thinking about this, can we source some of this natural gas rather than pulling it from underground rock formations? Can we make it through biological processes or capture it from landfills, agricultural facilities, things like that? And I think that is an interesting direction. I think it, again, hasn't really been figured out at the kind of scale that we would need here. And the biosources of methane that we kind of have existing today are fairly small, but you could imagine building them out significantly. And the big idea there is that you could have something that's close to a carbon neutral cycle where you do some biological processes, grow a bunch of crop or something like that, convert it into fuel, and then you release the CO2 and so forth. But basically, I think we don't know exactly what this would look like. Right now, the most cost-effective way to decarbonize in the electricity sector is to build wind, solar, and batteries, which get us potentially a quite significant way towards zeroing out the emissions from the electricity sector, but probably not all the way there. And so I think that last mile kind of thing, the last 10, 20% is still kind of up in the air. And it probably is going to require a mix of technologies, and some of them we might not really have today. Good field for bright engineers to work on in the future. And thank you for the questions, by the way. So if we take the green wedge here, the renewable wedge, and just blow it up and then look at what comprises that renewable generation. So first of all, we can see that there's some growth between the 50s and the 70s, plateaus for a long time, and then we see an uptick around 2005. And traditionally, all of the renewable power generation on the grid was hydropower, so dams and things like that. Around 1990, we built out some biomass-based electricity generation, so grow a crop, use it to create a fuel, burn the fuel in a power plant. And then wind took off, and this is really the most probably significant clean energy story in the US for the last roughly 20 years, since about 2005. And then solar, again, is about 10 years time shifted in terms of its adoption curve from wind. But solar, I guess I can move this, a little hard to see, has kind of taken off more recently. And so in terms of electricity generation, solar is catching up with wind and has really high potential to continue doing so. Yes, question.
Where does geo for uses like in building energy loads fall? I know this is a different type of geo, but what piece of the pie would that fall in? Is it more on the consumption graph than the generation graph, or where does that lie?
Yeah, so the question is, where does geothermal energy lie when it's used not to turn a turbine and generate electricity, but used maybe for direct heating applications in a building or an industrial facility? It's a good question. Certainly it would show up on like an energy chart. So if we go back to that Sankey diagram for the whole US economy, there was a small sliver that had to do with geothermal. It probably wouldn't show up on the electricity chart here. Yeah, yeah, I think that's right. It is kind of tied to the local application, whether it's used to heat up beer in a brewery or something that, not that you want hot beer, but heat up beer products, things like that. So yeah, I think that would be more kind of in the direct use portion of the graph. Okay, so I showed this on Tuesday. This is, again, a sketch of the electricity generation system and transmission and distribution system that kind of more or less is still the way that we do things today. And for most of the 1900s, this was the case. So again, we have a big generator, step up for high voltage transmission, step down for safe distribution, and then step down again for use kind of in the edge of the grid, which is really where our focus is in this class. And again, I just want to put numbers on this, but the reason that we do this high voltage transmission has to do with minimizing the losses of electricity over power lines. So the power transmitted by a current, I, so this would be in units of amps, at voltage V, in units of volts, is equal to P, is equal to the product of I times V. So in a direct current system, this would just be the current I and the voltage V. In an alternating current system, this would be what's called the RMS, root mean square current and voltage. So if you take those products, you get power. This is basically the useful power that is transmitted over these lines. And then the losses, the power losses over these lines can be expressed as I squared R. So this is called either resistive heating or Joule heating. So you take the square of the current, multiply it by R, the resistance of the lines, and you get the power that's lost essentially to heat over the transmission system. So if we do a little bit of math, we assume that we're trying to transmit a given power P, so call it 100 megawatts or something like that over a big power line. And the materials that make up the line, we'll say, are fixed. So it's going to be some copper, some aluminum, something like that. And we don't really have control over the resistance of the lines. And we want to minimize the power loss, this PL term. So in order to do that, we want the voltage V to be very high. And here's the math that shows that. So we take the definition of the power loss from the Joule heating, the I squared R losses. If we take this top equation, we can write that in terms of P and V. Basically just divide the right-hand side through by V here. So substitute that in for I, and we get a P squared over V squared multiplying R. And in this setup, basically the power P that we're trying to transmit and a resistance R of the line, these are more or less beyond our control. So this thing scales like 1 over the voltage squared. So if you can increase the voltage that you're transmitting at by a factor of 10, then you decrease the power loss over the lines by a factor of 100. In other words, you remove about 99% of the losses. Okay. So this basically allows transmission over long distances. So this simple fact influenced the evolution of power systems in the US and more broadly around the world. So I want to give a little bit of history here about the hardware that underlies at least the early history of the US power system. So in 1882, Thomas Edison built, he was called the Wizard of Menlo Park. His lab was in Menlo Park, which I guess is in New Jersey. But the first place that they built out a power grid was in Manhattan, one of the densest places in the world. And they used coal-fired steam turbine generator power plants. And 6 of them kind of located in various places near the same kind of part of the city. Each of them were about 100 kilowatts. So in today's terms, that would power maybe 20 air conditioners on a hot day. But back then, this electricity was used mainly for lighting. And so it, again, allowed stores and homes and things like that to stay open into the evening. And this was a really cool thing. It also allowed cities to basically replace gas-fired street lighting with electric lighting and things like that. And they use low voltage direct current lines, 120 volt DC. And this limited transmission, if you look at, you say, I don't want to lose more than, say, 20% of the power that I generate in transmission to the demand. It basically limited the length of wires that they could use to about 1 mile. So in this kind of early Edison vision of what the electric grid looked like, you would have small power plants kind of in every maybe couple of city blocks within Manhattan. And then you'd have short power lines bringing that electricity supply to the demand. Okay, so that was kind of the earliest technological development. scientist or engineer, I think named Charles Parsons in the UK, around the same time frame, basically came up with a new design for a steam turbine generator that used what's called multi-stage expansion in multiple turbines. So rather than having super duper hot, super duper high pressure steam flowing through one turbine, you might have it flow through a high pressure turbine and then get rerouted into a medium pressure turbine and then a lower pressure turbine. So this multi-stage, for various reasons, led to kind of scalability. So it basically, Edison, the biggest generators he could build and use realistically were about 100 kilowatts. And this allowed scale up to orders of magnitude beyond that. And I think Parsons in his lifetime, he saw his invention basically get scaled to the kind of hundreds of megawatts. So 1,000 times bigger than what people could build before his innovation. So this is one of the major innovations that led to kind of the grid being the way that it is today. Another had to do with developing alternating current power systems. So Nikola Tesla, around 1888, prototyped the first alternating current power grid. And the really key innovation that it included was the transformer, which is a way to basically step up or step down the voltage at which power is transmitted. So this allowed basically transmission at high voltage. Again, if you increase the voltage by an order of magnitude, you cut the losses by 99%. So this allowed long distance transmission lines with low losses. And Tesla was the inventor. His business partner, Westinghouse, used this technology to run a line 26 miles. So again, 26 times longer than what Edison was capable of doing with the direct current system. This ran from a big power plant in Niagara Falls to Buffalo, New York. Okay, so now we have the key innovations. We have the ability to build really big centralized power plants, and we have the ability to transmit electricity at high voltages over long distances. And so it wasn't actually for a while, about a decade, until a person named Samuel Insull, who had been Thomas Edison's secretary for about a decade, basically put together these two innovations: big power plants and long distance high voltage power lines. And he did this in the Chicago area, building megawatt scale turbines and transmitting over 9 kilovolt AC lines. And so this model really was the winning model of technology for most of the 1900s, using big turbines, high voltage AC transmission. And it was replicated not necessarily by Insull, but by competitors in other businesses and in other cities kind of across the US. And of course, there have been technological innovations since then. So solar panels and wind turbines didn't really exist in 1903, neither did nuclear power plants, right? We hadn't really discovered how to split the atom and things like that. But this basic model of a big centralized infrastructure and high voltage AC transmission was the winning model for essentially an entire century. Okay, so why did that win? Well, the main reason is that, again, we talked about this a little bit at the beginning of class, but basically economies of scale. So rather than building, say, I don't know, if you wanted to get up to, say, 100 megawatts of power generation, rather than building 1,000 of these small 100 kilowatt generators, maybe you can build 10 generators each at 10 megawatts. And being able to do that, you only have to go through the siting, land acquisition, permitting, engineering design, all these processes, right? Safety validation, commissioning, things like that. You only have to do 10 times rather than doing them 1,000 times. And so there are big savings in terms of those upfront costs. And same with the transmission. So if you have to buy rights of way to string 1,000 short power lines, it's going to be a lot more burdensome, slow, expensive than if you only have to secure right of way for maybe 1 or 2 gigantic high voltage power lines. Okay, so that's on the engineering side. And then I want to talk a little bit about kind of the business and eventually the government regulation side as well. So if we go back to that same time frame, the late 1800s, when Thomas Edison was active and building out the first power system in New York, there were basically, big business people. The term of art used to describe them as the robber barons. You probably remember from like a high school social studies class talking about these guys, right? But John D. Rockefeller is a famous example. So he brought almost the entire US oil industry consolidated under the control of about 10 people, the board of directors of what was called the Standard Oil Trust. So essentially monopolized the entire US oil industry. And that was maintained in similar form for decades until federal legislation basically broke up, and antitrust legislation broke up Standard Oil and converted it into a bunch of smaller companies, including Exxon, Chevron, and some other oil companies that are active today. Okay, so that was on the oil side. Also on the railroad side, there was really significant consolidation driven by J.P. Morgan, father of the bank, still known today as J.P. Morgan Chase. Not done directly by him, but in basically consultation with a lot of people who owned rail companies. He sort of coached them through how to buy up competitors and consolidate until you had either oligopolies, small number of companies controlling a whole industry, or monopolies, basically one company. And that led to all the stuff that you might expect when you're a captive customer and you only have one person to buy stuff from. They can kind of mess with you if they want to. And a lot of that happened, and it made people pretty unhappy. So there's price gouging, which is basically charging unnecessarily high prices for services or goods. And then price discrimination, which is giving basically friendly low prices to your friends and predatory high prices to your competitors or business enemies. And that led again to a lot of protest and to a lot of strike, and really, unionization and strikes were a big theme of this time period historically as well. And that public backlash, basically against really rail companies, led to the first really significant piece of legislation for regulating an oligopoly or monopoly business sector in the U.S. And that was the Industry Commerce Act in 1887, which was created to regulate the railroad industry specifically. But it basically gave inspiration for models that would later be used in order to regulate the electric industry. Okay, so that's kind of what was happening in this time frame in the economy more broadly and society broadly, specifically in the electricity sector. So we have this guy, Samuel Insull. Actually was a really interesting character, and it's kind of fascinating to read about. But he was Edison's secretary, who then later went on to become one of the major businesses in the run some of the major businesses in the electric sector in this era. But he bought out, again, in Chicago, he had this killer model, right, of using gigantic generators and really high voltage, long distance transmission to provide power at a cost that was really much lower than what his competitors were able to achieve. So he basically bought up all the competition in what we now call Chicagoland, the greater Chicago area, and formed a company that is still the major electricity supplier in Chicago called Commonwealth Edison, or ComEd. So is anybody from Chicago area? Did you ever pay a ComEd bill?
Well, I just know ComEd, I worked with them.
You worked with them, okay. Yeah, they're still a big player in energy in this area for sure. Okay, so actually there was really quite a time shift between the 1880s when oil was being consolidated and monopolized and this kind of era when Insull basically tried the same thing with electricity. And he did for a while. So he bought up his competitors and was able to monopolize the Chicago area, and other people, not Insull, but basically people doing similar things in New York area and Detroit and other major cities basically did the same, monopolizing electricity supply. But in parallel with that effort, you also had a lot of municipalities, so town and city governments, who decided that electricity was a public service, similar to other public services that they provide, like water supply, sewage, city lighting, maintaining roads, things like that city governments do. And so some of these city governments decided that they would do electricity supply themselves. And about 1,000 municipal grids were built out in roughly the first decade of the 1900s. And this was about a third of all of the power suppliers in the United States at the time. And generally speaking, there certainly were issues with corruption. This is also the era of like Tammany Hall and the big political machines, if you remember these things from social studies and history classes. Anyway, there were issues with municipalities, but broadly speaking, they provided reliable service at a reasonable cost. And they were publicly owned, so they're nonprofits. And so they basically posed a credible threat to the monopoly electricity companies. And so there was this competition, right? There was this kind of ideological and political and social and economic and business competition that was saying, this new cool service that everybody wants, lighting, clean water, all that kind of stuff that electricity enables. Should it come from private monopolies or should it come from public municipalities and things like that? And these companies basically saw the writing on the wall, and they saw the credible threat that these public utilities were posing. And so there was a compromise, a grand bargain that was made, basically, in order to avoid these monopolies essentially being municipalized, taken over by cities and run by governments instead. By the way, all of this that I'm talking about comes from a history book written by, his first name is Robert Hirsch, but called Power Loss. And there's some long subtitle there. It has to do with deregulation and kind of the history of the US electricity sector. It's quite fascinating. And if you can get a copy of it, I think the first couple of chapters of it are really interesting kind of outside reading. But this all comes from chapter 1 of that book. Okay, so then out of this kind of conflict and then bargain, we saw basically public regulation of the monopolies that were running electricity supply in most of the big American cities. So the first example of that came in Wisconsin, a couple states north of us. This Wisconsin government created public commissions to regulate various monopolies. So not only electricity, but including electricity. And so the vision there was that basically the monopoly companies that had bought up all their competitors were allowed to exist. In fact, were embraced by the state. But they basically gave some control of their operation over to the commissioners who were either appointed by governors or elected by voters. So let's talk a little bit about that compact, that grand bargain of regulation, what different people got in that. So people got some control over pricing. So they ended kind of the price gouging and the price discrimination. They got some visibility and transparency into the monopoly business practices. They also got the obligation, essentially a commitment to pay enough money into the system so that those companies could stay afloat economically. And then the companies got a lot of benefits as well. So they got, first of all, state guaranteed protection from competition. So they didn't have to worry anymore about someone coming in and starting a new competing business in their service territory because they were guaranteed monopoly rights. They were also guaranteed returns on investments by the state. Basically, if they build some hardware, costs some money, they have to take out a loan on that. They're guaranteed that they can pay back that loan by getting money from people who pay utility bills. So there aren't very many investments that you can make where a government says, no matter what happens, if it goes well or it goes badly, I guarantee that your investment will be profitable. They also got the use of eminent domain. So this is typically a state power that can use to either force people to give or sell their land for purposes that are deemed critical by the government. So this is often used for building roads, water infrastructure, things like that, but was also used to build out, for example, long transmission lines that had to go through people's farms, yards, things like that. And a little bit less tangible, but they got legitimacy kind of in the public eye. So rather than being, a predatory monopoly that was charging you too much money for the electricity that you bought, they became sort of sanctioned as public goods. So necessary services that are provided by companies that are sort of doing a good for the world. And companies, in addition to getting all these privileges, got an obligation basically to provide reliable and affordable electricity to everyone in their service territory. So universal service. Yes.
Does the guaranteed return, I might must have missed this, but does it come directly from like the government and subsidy, or does it is there a stipend where you can raise the rate?
So the question is, where do the guaranteed returns on hardware investments come from? And the answer is through raising prices on people. Yeah. So it's not through tax revenue by the state, for example, but it's through sales of electricity. Yeah. So if you have a really expensive, really bad investment, rates are going to go up for people, basically.
That's a good investment for me.
Exactly. And so that's where for folks online, you have to do sort of your due diligence to show that whatever you're investing in is going to be prudent, right? Financially likely to return, to work out and return a good investment. And so that's where kind of the oversight, the public oversight comes in. Basically, if a company wants to invest in something or wants to raise prices, they need to justify why they're doing it. Right? Okay, so that's kind of the nature of the bargain here, at least in theory. But actually what happened in practice was almost immediately the managers of these big companies began to influence their regulators. So they influenced public opinion, which of course shapes what the electorate cares about and who gets elected. And they did that through press releases, through speakers at events, by influencing the curricula that were taught in high schools, colleges, and so forth. For example, by sponsoring professorships at universities. They gave donations, often very significant donations, either to the governors who appoint commissioners in about 40 states, or to the commissioners who campaign in about 10 states they're directly elected. There are some funny examples in the early days of wining and dining commissioners and basically getting them drunk and convincing them to do things that are favorable for the company. This is, by the way, now codes of ethics typically ban most of these things, but not all of them. And then there's what's called the revolving door. So, if a commissioner is in office for maybe 2 to 6 years, something like that, what are they going to do after? They spend a significant chunk of their career just learning all about this one weird, complicated business. Well, it's kind of natural that they might go to work for that business as well. But you can imagine how that brings in some conflicts of interest potentially in terms of these regulatory decisions. Anyway, so this stuff is not all true today, but some of it remains true today. But so there are alternatives to these kind of regulated monopoly utility models in the US. This is the mainstream model that serves about 75% of Americans. So this is a map basically of where investor-owned utilities are in the US. There are also some public utilities that take a couple of different forms. One is a lot of those municipal utilities that formed in the early 1900s are still around, and they serve about 35 million people in the US, as towns and cities. And then also there are some federally owned, so not state or municipality owned, but owned by the federal government, power generation transmission services. And so one of those was created by FDR. This is the biggest one, the Tennessee Valley Authority, or the TVA, I guess in this region here in Tennessee, and touching on, I think, half a dozen states around it. And then in 1936, kind of in the post-depression era, FDR passed what's called the Rural Electrification Act. Basically, it's expensive to run long power lines out to sparsely populated areas. So companies were not bringing electrical service out to farms and things like that. So FDR basically put people to work and put a lot of money behind running electrical wires out to rural areas. And so actually, if you look at the Lafayette area, kind of a donut area around Lafayette is actually run by one of these rural co-ops called Titmont REMC, a Rural Electric Membership Cooperative. So these are nonprofits that are member owned and member run, and they basically, provide power supply for folks in rural areas. So roughly the 3/4 of the US is served by the investor-owned utility, and the remaining 1/4 is either public or co-op. Okay, I'm probably not going to have time for everything, I'm realizing, but that's okay. We can talk about some of this next week as well. So I think that regulatory compromise that came out in the early 1900s more or less stayed in place until the late 1900s. And then there were a couple of laws that were passed federally that sort of shook up that relationship. So typically we had what are called vertically integrated monopolies, one company that owned all the power plants, all the high voltage transmission, and all the medium voltage distribution lines. But in 1978, something called PURPA, passed by Carter, the Public Utility Regulatory Policies Act, basically made it so that other companies could build generation and maybe using different technologies and things like that. And the companies that owned the transmission and distribution systems were obligated to basically buy power from these other companies. So that kind of broke up a little bit the generation side. And then in 1992, the end of the George H.W. Bush, Bush 1 era, the Energy Policy Act was passed, and that basically opened up, or laid the groundwork to open up the transmission system to competition. And so today, most high voltage transmission in the US is run by nonprofits called TSOs, transmission system operators. And they run wholesale electric markets where generators can basically offer power, and utilities can say, well, I need this much power. And they basically do a clearing process to match supply and demand in a market. And they're also charged with ensuring reliability of electricity supply. So a TSO is often called an ISO, an ISO, if it only operates in one state. And if it operates in multiple states, typically we would call it an RTO, a regional transmission organization. And then we still have some utilities that own both generation and distribution. So they have the G and the D, but not the T. But also we have other power plants who can sell electricity into wholesale markets. And we have other companies in about 13 states. You have retail competition. So you can choose who you buy your electricity from for your home or for your business. And the idea there is that there are some third-party companies that basically can buy electricity wholesale and then pay for the use of the power lines that the distribution utility owns, pay them some nominal charge, and then deliver electricity to customers, potentially at a lower cost or cleaner power or something like that. So this is just a sketch of what the vertically integrated model looks like. So we have basically the hardware from generation all the way down through load. The user owns the load typically, and then you have one company, a regulated monopoly, who owns all the generation, transmission, and distribution. And then they have a state regulator, and there's exchange of information, permission to build stuff, to raise prices, things like that. And then in the wholesale model, we again have the same hardware stack, and we have the same user owning the load typically. But then now the company that the regulated monopoly probably only owns the distribution. They may own a little bit of generation, but not all of it. And then we have a transmission owner, a generation owner, and these are all connected by the TSO, so either the ISO or the RTO. And then we still have the state regulator over here as well. And so these guys basically provide a market that takes in money via monopolies from ratepayers and then disperses it to the people who own the generation and transmission systems. So here's a map of the TSOs in the US. So some states have their own. California runs what's called CAISO, the California ISO. New York also has their own, and Texas has their own as well. And then we have many that span multiple states. So New England ISO is half a dozen states in the Northeast. PJM is much of the Eastern Seaboard. This stands for Pennsylvania, Jersey, Maryland, but also they cover many other states. And then we are in the MISO service territory, Mid-Continent ISO. Actually, the headquarters of MISO is about an hour from here in Carmel, Indiana. And then let's see, there's the Southwest Power Pool and the Western Power Pool. And then this, I think, is Ontario. Canada has its own ISO as well. And then the regions that are white on this map are basically places where we still have vertically integrated utilities providing kind of all three of the generation, transmission, and distribution services. Okay, so the TSO has various kind of operational problems that they need to solve in order to basically make sure that electricity supply and demand are balanced at timescales ranging from fractions of a second all the way up to decades. So at the slowest timescale, they have what we call capacity planning, which is, basically you forecast how much electricity demand is going to grow over the coming years, and then you decide what is a cost-effective and reliable way to meet all that demand growth by building new transmission, building new generation, and so forth. Timescale is kind of on the order of weeks or months. We have maintenance planning. So for example, a nuclear power plant might need to come down for a couple of weeks per year to do refueling and safety checks and things like that. So you want to know when a huge generator is going to go offline and plan accordingly. Unit commitment is kind of at the scale of days to weeks. And the idea here is that it takes some time for something like a big nuclear plant to shut off or to turn on. And so this is basically deciding which power plants and other resources should be kind of ready to go to be turned on to meet electricity demand. And then economic dispatch happens kind of at the scale of hours to days. And the vision here is basically figuring out of those resources that are turned on and ready to go, which ones should actually run to generate electricity and reliability services in order to operate the grid in a cost-effective and reliable manner. And then there are control problems kind of at faster timescales that have to do with safety, reliability, robustness to cybersecurity, but also maintaining the frequency on the alternating current grid at its nominal value, 60 hertz in the US or 50 hertz in Europe and much of Asia, and then maintaining voltages at appropriate levels kind of throughout the grid. Okay, so in this class, I think really it's kind of this time scale here in the sort of hours to days time scale is really most of our focus in this class. So I want to zoom in and talk a little bit about how that economic dispatch problem works. And so again, this problem basically is, you have a number of resources that could be generators, batteries, things like that, flexible demand resources that are ready to go. And you want to match supply and demand, looking ahead, say, a day into the future. And you get offers from various resources. And they say basically an offer has the form of an energy and a price combination. So this is one generator, maybe a big one, that says I can generate this much energy. And if you take that offer, I will request you to pay me at this price. Here is a smaller, right? So less energy, but also lower cost generator. So shorter rectangle. Here's a pretty big, but also pretty expensive generator and so on. So you can imagine one way to solve this problem, setting aside things like transmission constraints and so forth, is basically to rank these in what's called a merit order. So you rank them in terms of the price that they offer. So the lowest cost resource, you say, has the highest merit. The highest cost resource has the lowest merit. And this thing here is the descending order of merit. And then you obtain demand forecasts from all the different utilities who want to buy electricity for their customers. So if you have this generation stack in the merit order, and if you have this demand forecast, what should the grid operator do in order to basically provide electricity as cheaply as they can? So which of these power plants should be turned on? Any thoughts? Yeah, the ones to the left of the demand line, right? So this is what it looks like, basically. So all of these generators would get dispatched. And then this one here is what's called the marginal resource. So basically the last resource that gets turned on in order to meet demand. And all of these guys, the prices were too high. So they do not get dispatched. They don't get paid. Yes.
Can you buy at like a part of from the marginal? Or do you have to buy it all? It's like if you want to do the fourth one, you have to buy it all.
Yeah. So the question is, can you only take a portion of the offer? Or do you have to buy basically the entire block here? And the answer is that, yeah, you can take a portion of the offer. So if I say, basically my offer says I can produce up to 100 megawatt hours, but I might only get dispatched to actually produce, say, 10 or 15, something like that. So that does happen, yes. Yep.
Isn't that kind of hard depending on what you're producing? Like if it's nuclear, it's like it takes a while to ramp up and if they're like, oh, we'll only buy it for like 2 hours, then are they just gonna like reject it and say, yeah, it's not really worth it?
Yeah, so the question is, isn't that kind of hard to do in a real market where you have physical constraints, something like a nuclear power plant that can't ramp up or down very quickly, right? It's kind of either I'm producing at my full capacity or I'm just going to shut down, something like that. So yes, and that's one reason why we see deviations from the merit order, this kind of idealized ranking of least to highest cost resources. So you might basically, when you submit an offer, you might say, but I can only do, but I must run for at least 8 hours or at least 4 days or whatever it might be. And then those enter as basically constraints in this decision problem or optimization problem. And then they affect the way that plants are dispatched. So yeah, this is kind of a stylized view, the merit order view. And in real power systems, they don't work exactly this way. It's kind of a first order heuristic for understanding what we're trying to do, and then understanding deviations away from that lead to higher cost systems. Okay, so I was going to ask this, but I guess I'll just say, well, let me ask. So what price do you think each of these generators should be paid? So this is a low cost resource, a medium, and a higher cost resource. So what should we pay them after we decide that they should run? Any thoughts?
No.
Well, I guess they've all submitted prices associated with their offers, right? So I say I can produce 100 megawatt hours at $3 per megawatt hour, something like $30 per megawatt hour, say. And anyway, okay, so we're getting to the end of class, so I guess I'm just going to jump to the answer. So the way that this is resolved in US power markets is that the marginal resource sets what's called the clearing price for the market. So everybody, even a cheap generator that only needed, maybe 1/4 of the payout that this guy needed in order to kind of stay afloat, this generator gets paid at the clearing price that the marginal resource sets. So another way to do this would be to say, well, you offered it at $10 a megawatt hour, so we will pay you $10 a megawatt hour. That would be another way to do this. But for whatever reason, this is the way that US power systems work. Question?
So you're incentivized to create cheaper power because you can make more margin if you make the clearing price either way.
Yeah, so the suggestion is that you're incentivized to basically produce lower cost power. And I think that is right. So there's one incentive, which is that you want to get dispatched, right? You want to be low in the merit, or high in the merit order, or low in the stack, so that you're likely to actually run. If your power plant, produces really expensive power, you never get turned on, you're not going to make much money. So that's one reason you want to make a low offer. The other reason is, yeah, there's basically a gap between what you get paid and what you offer. So even if you submit a low price, you're sort of gambling that you're not going to be the marginal resource, and that the marginal resource is going to be more significantly more expensive than you are, so that you can make up the difference here. Yeah. Yes.
Then why would someone produce like the larger power plant, like not a larger power plant that is you cannot run from the So
why would someone build a really large power plant in this scenario is the question. Well, so big often, again, due to these economies of scale, big often correlates with cheap, right? So you might need a bunch of money up front to build a really big plant. But then once it's there and running, a nuclear power plant, something like that, has fairly low fuel costs. So they might not need very much money as a payout in order to basically pay off their investment. So you might have a low cost power plant that's producing very high volumes of power. Yeah, so this guy, if this one was much, much bigger, I guess you don't want to get too big to the point where you become the marginal resource. at that point, you lose this gap basically between you and the more expensive generator that sets the price. Yeah. We are at time, so there's more that I want to talk about on this, but I think we'll pick up around here on Tuesday, and then we'll continue with the first sort of more technical lecture of the semester. So any final questions before we wrap up? Yes? Yeah, do I have a recommendation for some reading on the kind of policy stuff that we talked about earlier outside of this book? Not off the top of my head, but I will put something up online. Yeah, thanks. Good question. Yes?
The Slack channel thing, I think I clicked it, just said it was down, I don't know if you're still.
Yeah, so the Slack channel, we had a weird link on the website, I think, but we have updated that. And so RTA not updated that. So I think you should be able to join now. If not, shoot me or actually shoot RTA an email. I think that'd be easiest. But yeah, the link is updated on the website. All right. Well, thanks all for your time. Have a good weekend, and I will see you on Tuesday.